Today we're going to take a look at section 3.6. It's called optimization. Optimization in general means trying to find the best something. You're trying to optimize whatever. So maybe it means you're trying to find the biggest area that you can plant your garden in. Maybe you're trying to find the smallest amount of money you can pay for a specific kind of product. So that's kind of a business application. We're not going to get into too much business applications, but there are business applications with this too. We're going to be looking mostly at geometric kinds of things when we're looking at our optimization. So to start with, there are some guidelines for optimization. The first thing you see is it says to make a visual. Sketch, table of values, etc. So a lot of times it's going to be a sketch for us. The second thing to do is to identify what you know and what you need to find. The third thing is to write out an equation. And it's often an equation you just already know. Like if it talks about, for instance, the area of a circle. You should know the area of a circle. But if you don't, it may mean that you have to look something up, Google or flip to the front or back flap of your book or something like that. Okay? So some equations that you know. The other thing here it says is identify what quantity is to be optimized. Now, let's say, for instance, you have a shape of a circle. Okay? Well, a circle has both area and perimeter. It also has the radius of it. Okay? So there's three different quantities there in terms of the circle, and we got to figure out which one it is that I'm trying to maximize or minimize, hence optimize. And it's not always the same quantity depending on the context of the problem. And then the fourth thing is to figure out, determine the maximum and minimum allowable values. I'll show you what that means when we get to that particular point. But just because in mathematics you can get an answer of -1 doesn't necessarily mean -1 makes sense in the problem when it's a real world problem. Make sense? So there are usually constraints upon which you're allowed to give values with a problem with application. And then, of course, number 5 says use calculus to find the extrema. It's the shortest one. Oh, wait, maybe the first one's the shortest one. It's one of the shortest steps, but it's actually one of the ones that takes you the longest because that means taking the derivative, setting it equal to 0, using a sign chart, and so forth. Okay, it's just short to write. It's longer to do. We're going to do an example, and this is an example that you have probably seen done without calculus before, and that's fine that you've seen it be done without calculus before. I'm going to show you how to do it with calculus, just as a beginning example of how this can be used. Okay? So, our first example is we have a 3-sided fence, and it is to be built next to a straight section of a river. The river forms the 4th side of a rectangular region. So the first thing we're going to do is we're going to draw a sketch. Yeah. So we've got this river over here. It's even blue. And then we're going to draw this rectangle, the other 3 sides anyway of this rectangle, next to it. Well, it's not perfect, but you have a visual idea of what we're doing here. So tell me something you know about the sides of this rectangle already, without reading any more into the problem.
Length and I'm trying to think of it. 2 sides are going to be equal.
Right.
To another side.
Yeah, and the way I've drawn it, it's the one that's on top and on bottom, right? So they're opposite sides, or you can call them non-adjacent sides. They're going to be the same. So whatever's up here is going to be down here, and I'll call it X. You can call it whatever letter you'd like. And then the other one, I'll call it Y, may or may not be the same, and so we need a different variable for it. Does that make sense? I mean, and technically you have another Y on the other side, but you're not putting fencing over there. So we don't need to mark it in any way. We're marking only the fencing. All right, let's go back and keep reading on the problem now. It tells us that the area that is enclosed is equal to 1,800 feet. So we actually know the area here, and I said feet, I meant to say square feet, 1,800 square feet, or 1,800 feet squared. And then here's the question that I'm asked. I'm asked to find the minimum perimeter and dimensions of the corresponding enclosure. But in particular, the phrase right here that I'm kind of keying in on, or should be, is the word perimeter. So we actually know the area in this problem, and we're asked to find the perimeter. That's kind of backwards of the way this problem is typically presented to someone. Usually they tell you, I know the perimeter and I want to find the area. So be careful to not sort of be led down the path that you've seen traced before, right? I mean, make sure that the problem really is what you think it is. All right, so this one wants us to find the perimeter, and we know the area. So let's actually take a look at equations that we can set up for area and perimeter. So what can you tell me about the equation for area for this diagram? Length times width, and in terms of the letters that I've used, it would be x times y. And the kicker on this one is that we actually know this equals something. It's 1800. So we're going to need that piece of information in a moment. The second piece of information is perimeter. What is the perimeter of this figure as drawn? 2x plus y, right? And we don't have an equals something on this one because we don't know what it equals. That's what we're trying to find, right? So this right here is what I'm trying to optimize. And I'm wanting to optimize it to be a minimum. Okay, and I'll bring that back up in a minute when we get there. All right, so to optimize, we know we need to find a derivative, but right now, my perimeter equation has two variables in it. And you do not have the material that you need at this point in calculus to deal with that being two variables. That's Calc 3. I'm not there yet, okay? So we need to do something to get rid of one of those variables. What do you think we should do?
Write x as y.
What's that?
Write x as y.
Okay, from where?
From the area.
Perfect. All right, this area equation that we started out with up here is a wonderful expression of x and y's relationship to the number 18. So we can take either x or y and we can rewrite it as x equals or y equals with the other variable on the other side. So which one would you like to solve for? X? All right. So what will x equal? 1800 divided by y. And our whole point in doing that is so that we can take this quantity and plug it in right here for x. So this now becomes 2 times 1800 over y plus y. So far so good? And this is equal to perimeter. I'll put equals p over here. Let's clean this up a little bit. 2 times 1800 would be 3600, right? And I'm going to write this as y to the negative 1 and then plus my y. All right, let's go back over here for a moment and think about this particular diagram. This particular diagram has area that's 1800, right? So what is the smallest value that either x or y can be? I mean, it can't be smaller. Well, it could technically be smaller than 1. It could be like 1/2 or something, right? But it couldn't be 0, right? So for sure, the minimum value for x or y is 0. So 0 is going to be strictly less than my x or my y. But x and y also have caps of what they can be. Agreed? You have to think real carefully. Don't be sucked into the trap of thinking about perimeter here. This isn't perimeter we're talking about. We're talking about the area. So if we have the area of something, well, at the very least, you know it can't be bigger than 1800, right? Actually, that's not quite true even, because it could be if I had 1/2 or something like that. So this one may just be capped like this for now. We may have to have just that detail for it for now. We'll come back and look at it when we're done. So these are some constraints we have. That's our constraints for now. Okay. We are at the point where we are on basically step 5. What does step 5 say that I'm going to do? I'm going to use calculus. Okay, so what am I going to do? Somebody said it over here. Find the derivative, right? Okay, so what is the derivative of 3600 y to the negative 1? Okay, negative 3600 y to the negative 2. And the derivative of y? Plus 1. Okay, with calculus now we have found the derivative. What are we going to do next? Can't solve for y yet. Got to do something else first. Set it equal to 0. Yeah, and then I can solve for y, right? All right, so set equal to 0. I've actually got an equation now that can be solved for y. In particular, I might decide to move the 3600 over here just so that everything's positive. Something like that. I've got a y to the negative 2. Can I put that back down in the denominator? Sound okay to you? All right, so I'm going to actually put this over y squared. What would I do next?
Multiply by y squared.
Sure, we're going to multiply by y squared so we don't have it in the denominator any longer. So over here, those cancel. So now I have y squared equals 3600. Now what? I take the square root. Now technically and typically when we take a square root we would put a plus or minus, but I don't need to do that here. Why? Y is only positive. Can't have negative side lengths. So it's something to be aware of, and that's why we looked at that earlier. So what is the square root, the positive square root of 3600? 60. Okay, so back in my picture now, I have found that this one is 60. What would x have to be?
1800 divided by 60.
Yeah, 1800 divided by 60, right? So x is 1800 over y. That's 1800 over 60, which gives me what? 30. So I've got 30 here and here now. And it's all measured in feet, so let me write feet everywhere. You wouldn't necessarily have to go back and put it on the diagram. I just am. So we do need to answer the question. When we've found something, we found either a maximum or a minimum, we think. We actually just found a critical point, right? So we do need to verify that it really is the point that I'm supposed to be looking for. In particular, if I draw a number line and I put the x or the y value on the number line at 60, and then I use the derivative, which is here, I need to test a point smaller than 60 and a point bigger than 60, but it can't be smaller than, it can't be 0 or smaller. It needs to be something larger than that. Okay? So maybe you decide you're going to test, I don't know, 10 and 70 or something like that. So go ahead and put one of those numbers in. Somebody put a 10 in for me, somebody put a 70 in for me, and I need into the derivative, the part that's outlined in blue, and figure out what we get. What happens when I put a 10 into negative 3600 over y squared plus 1? Did you do 10, Tristan?
Yeah.
Okay, what'd you get?
Negative 35.
Okay, and in particular, it's the negative we care, right?
Yeah.
It's negative. All right, has anyone done 70?
Yeah.
What did you do 70, Matt? What'd you get?
Positive.
A positive. So this is first derivative stuff. So this is increasing, decreasing stuff. So the negative means it's doing what? Decreasing. And the positive means it's increasing. So what's happening at 60? It's a minimum. Was I supposed to find a max or min? Minimum. Yay! That's good. All right, but this verifies that we found what we think we found. I mean, it really is, in fact, a minimum. So now we're going to answer the question. It says to find the minimum perimeter and the dimensions. Let's actually do the dimensions first. What are my dimensions? Right, dimensions are 60 feet by 30 feet, or 30 feet by 60 feet. What's my perimeter? Is it 120? Because I've got 3 sides, right? 2 x's involved, right? So my perimeter is 120 feet. So I've got 60 plus 30 plus 30. All right, any questions on that one? All right. Let's take a look at another one. This one's a very classic example of an optimization problem. A box with no top is to be built by taking a 6 by 10 sheet of cardboard and cutting X inch squares out of each corner and then folding up the sides. Find the value of X that maximizes the volume of the box. So we're going to start with a picture. The picture I'm going to draw first is what? A 6 by 10 sheet of cardboard. Even if you aren't sure what else is going on in the problem after that, I know you can recognize to draw a 6 by 10 sheet of cardboard. It's a long rectangle. The next thing it says we're going to do is we're going to cut x inch squares out of each corner. So we're going to cut corners out, and they're all going to be the same size corner, otherwise it's not going to make a very good box. Right? They're all the same size corner that we're going to cut out. And as I do this, after I cut them out, I'm going to fold the box. So I'm actually going to mark mine a little bit differently than it actually is being described to give us the image that we're describing as a whole. So what we've got going on here is we've got these four little corners of the box, right, that are being clipped out. They're not going to be a part of our box. And then after we clip out this corner and this corner, there's going to be this piece left in the middle here that's going to get folded up to form the side of a box. So the image of the box that you should have in mind is something kind of like a t-shirt kind of box. You know, I don't know if you've ever bought a shirt at a department store where they ask you, do you want that gift wrapped? It's that kind of a box that you're looking at where they flip up the sides, okay? So we know that there is supposed to be an original length right here of 10 and an original length right here of 6. And then the other thing we know is that we're cutting out these squares, and these squares have an inch length of x. So in particular, this piece right here is x, and this one's x, and this is x, and this is x, all the way around. All right, the side and the two sides of those are all x's. All right, so let's take a look at what it says next. It says it wants us to maximize the volume of the box. How do you get volume of a box? Length times width times height. So in general, the way I have volume here is length times width times height. Now right now my picture as it's really drawn is still a two-dimensional picture, so we have to use our imaginations a little bit to think about the folding to get our length and our width. Now take a look at what ends up being the base of the box. The box that remains two-dimensional, the part that remains two-dimensional, is the inside rectangle, right? What are the dimensions of the inside rectangle? Okay, this one right here, this is the one Edgar's giving me, is 6 minus 2x. Does everybody see why it's 2x? Got the x on each side, right? What about the longer piece? Right, 10 minus 2x. So that's sort of the length and the width, right, of my box. 6 minus 2x and 10 minus 2x. Let's pause for a moment and make note of the fact that x can't be just anything. What is the biggest value that x could be? Or what can x be no bigger than? Obviously x is positive. It can't be bigger than 10 or 6, you're right, which means 6, but it can't even be 6 big. 3. Where did 3 come from? Yeah, it's half the length of the 6, right? So if I cut in 3 inches from this way, I'd be cutting in 3 inches from this way, and I'll have no box. So I have to have my x be smaller than the value 3. Does that make sense to everyone? And it will feel like sometimes that this step is sort of unnecessary, but occasionally what will happen is you will get an answer that matches the equation that you've created, but it doesn't match the context. So you do have to make sure to be cognizant of the fact that this isn't going to work for every x that works for it. All right, so between 0 and 3. We have identified then that our length and our width, respectively, are 10 minus 2x and 6 minus 2x. What's my height? X. That's the corner that gets folded up, right? It has length. So now our height of x. Now, I know we have product rules, and that's great, but it's going to be a lot easier to just multiply this sucker out. Okay? So we'll multiply by the x at the end, but let's multiply the two binomials together first. So I have 10 times 6 or 60. My outside terms is negative 20x. Inside's negative 12x. Last term's plus 4x squared. All that's multiplied by x. So I have 60x. I can combine these two in the middle for negative 32x x, but times the x on the outside makes it x squared, and then plus 4x cubed. Now, the setting up and the visualizing and the details of this make it a little challenging in a different way than the other problem. But the nice thing about this problem is I only have one equation I'm working with. There is no question in my mind what I'm doing because I only have one equation to do it with. The other one I had to actually make decisions about volume and or area and perimeter and which one I'm doing what with. So that part of this is friendly. All right, so here's my volume. I'll just put V equals. What do I do with it next? Not yet. Ooh, you're so ahead of us. What's first? What is it? Take a derivative. All right, so let's take a derivative. Fantastic. What is the derivative of this equation? It's a polynomial. That's friendly. What do you get? 60 first. Okay, what's next? Uh-huh. And then, Matt, this is the one you were telling me. 12x squared, right. Okay, then what are we going to do, Tristan? They're going to set it equal to 0. Okay, so the setting it equal to 0 part, I'll go to my next screen. All right, we're going to set this equal to 0, and this is a what kind of function? Squared. So we call it quadratic, right? How do I find out where quadratic equations equal 0? How do I solve them? Factoring if we can. Quadratic formula if we can't, and completing the square if somebody makes us, right?
Yeah.
Yeah, okay. All right, so let's first notice that all of these numbers, 60, 64, and 12, are all even. So at the very least, they can all be divided by 2. Can we divide by something bigger than 2? I think they can be divided by 4. So let's divide them each by 4 and see what happens. So what is 60 divided by 4? 15? 64 divided by 4 must be 16 then, right? And then the first one is, or 3x squared. And I think some of you have probably already done it. I'll go ahead and rewrite mine with the order going from highest exponent down because it's bothering me. All right, that looks better. So it would be sad to use the quadratic formula if we didn't have to. So it's probably a good idea to try to factor it. But this one isn't going to factor. So I don't want you to think that I'm just jumping into the quadratic formula just because that's where you should jump in. You should try to factor, but this one's actually not going to. So we are going to use the quadratic formula. So do you guys remember the quadratic formula? I don't think we've done it in class actually together, have we? No? Yeah?
Yeah.
All right, somebody tell me. We're just going to write it out first.
Minus b plus or minus square root b squared minus 4ac and then divided by 2a.
Right. And we want to be careful that it is completely and all divided by 2a, including the b in the front. Sometimes people forget that part of it. A is, of course, the first coefficient, B is the middle coefficient, and C is the last coefficient if it's written with the highest degree down to the lowest degree. So for this function, we've got negative b. Well, the b in the middle is already negative, so this ends up being positive 16, plus or minus. Now I have negative 16 squared, so what is negative 16 squared, or 16 squared? Not the square root, the square. 256, right. And then I have 4 times a, which is 3, times c, which is 15. We'll do that in just a minute. And this would be all over 2 times a, which would give me 6. All right, let's simplify just what's underneath the radical first. What do you get when you take 256 minus 4 times 3 times 15? And I don't even know because I don't have it written down. From that value. I have a different one written down.
76.
76? Anybody else have a 76? Yep, Kayla does. Okay. All over 6. So back in the day, somebody told you need to look for perfect squares underneath radicals and clean this up in that fashion. And back in the day, that was true. And in actual purest mathematical terms, that is a very true statement, and that's what I'm going to do. But what kind of problems are we working on? Application problems of optimization, right? They're word problems. So my answer in all of this needs to be a decimal because that's what makes sense in terms of answering the question that's asked. So the beauty of that is that your calculator can simplify this for you and you don't have to do it directly. Now you do need to be careful because you will have potentially two solutions. One that's 16 plus and one that's 16 minus. Right? So these are my two solutions. So somebody tell me what happens when I do the plus one. What is 16 plus the square root of 76 over 6? Huh? 4.12. Awesome. And we will use two decimals. And how about the second one? 1.21. Everybody good with that? Are they both really potential answers for us? No. What's wrong with that first one?
It's above 3.
It's above 3. So it matters that we checked that, right? It does. So the answer, if the answer actually exists, is going to be 1.21. So what we want to do then is to figure out if that really creates a maximum, because that's what we're supposed to be doing, is maximizing. So how do we do that? Well, we do a sign chart with the 1.21 on there. We need to test the number before it, maybe the number 1, and a number after it, maybe the number 2, and we test it into the derivative. You got it. So my derivative is, a version of it anyway, is here, or you can use this one, or you could use this one. Any of them are fine. Any of those that are bolded in blue. They'll give you different values, but I care about the sign. They'll give you the same signs. If I put in the number 1, what do I get? A positive, okay? And if I put in the number 2? A negative. Again, this whole section is about derivatives, so it's looking at increasing, decreasing. Positive is increasing, negative is decreasing. Therefore, what happens at 121? It's a maximum. Now, you could also, if you didn't want to do a sign chart, test this in another way that would work really well for this particular problem by doing the second derivative. Polynomials are easy to calculate derivatives for, right? Really. So we could actually find the second derivative of volume here, which would be negative 64 plus 24x, right? And then we could evaluate that at our point 1.21. And if we do, we will get a negative. What does the second derivative being negative tell us? That it is concave down, and concave down means I have a maximum. So you could verify it that way as well. Doesn't make any difference. It's your choice. Sometimes that's an easy way to do it, and sometimes it's not. So, all right, so let's go back to the question as asked. It says, where did I get it? Find the value of x that maximizes the volume of the box. So it doesn't actually have to ask me to find the volume. So my value of x is going to be my answer. So x equals 1.21 what? Inches. There should be units because units were given in the original problem. All right, any question on that one? All right, the next one, a little different, says that we're going to find the point on the curve y equals x squared that is closest to the point 0, 1. So this is an application, but it's not an application in a real world type of sense. But there are different points in mathematics where wanting to find the closest point or something like that to a particular point is a really helpful tool. And so we're going to talk about how that would particularly work on this one. So what would I do first? Usually I draw a picture, all right? It's not like an absolute, if you don't do it, you're end up, up a creek without a paddle, but it's usually quite helpful. So this is the graph of y equal x squared. And on the graph of y equal x squared, there is the points. This is at 1, this is at 1. The point that I'm caring about right now is this particular point here in the middle that's blue. And we're wanting to figure out which point on our graph, maybe it's one of the two that I just marked, maybe it's not, is the closest to the point that I want. Now, clearly I could go straight down or straight left or right from where I am and be just 1 unit away, right? I mean, so if you want to think about it, the maximum answer here that is at all possible is 1. I know that I'm at least 1 unit away if I just go down 1 or to the left or right 1. So whatever answer I get had better be a number that's between 0 and 1. So my answer here had better be between 0 and 1. my distance. Let me say it that way. It's the distance away. I know my distance is going to be less than 1. Okay, so how do I know if that actually is the answer? I mean, I know that's possible. It could be just 1 away, but maybe it's closer. Well, it's distance that I'm trying to minimize, right? I want to minimizing the distance. How do I find distance? You guys remember, this is like age-old kinds of questions today, huh? Quadratic formula, distance formula. What in the world is she doing? What is the distance formula? Do you remember?
X.
Somebody said x, their square root.
Oh, yeah.
Okay.
I think this is what you were trying to get at. Does that look good? Yeah. All right, fantastic. So this is the distance formula, but we have some of this already. What values in this formula do we know?
X1 and Y1.
Yeah, we know an x1 and a y1 or an x2 and a y2. It doesn't matter where we put them. Since we're doing subtraction, I'm going to put them in as the x2 and the y2, just so that I don't have negatives on my variables. And while it's perfectly okay to have the subscripts of 1 on the x and the y, since I only have one x and y now, I'm just going to leave them off. So this is going to be x minus the x value, which is 0, and y minus the y value, which is 1. So far, so good? Okie dokie. So this is x squared. I kind of need to pause here and think about something. The formula before the line I'm on right now has an x and a y in it both, right? And when we're optimizing, we need just one variable in it, not 2. So is there a way that I can eliminate the y and turn it into something related to x instead? You can. We have an equation for the relationship between y and x. Y is x squared. So I can actually plug in x squared in place of y. And then I can square that out. Okay, so I've got the square root of x squared plus x squared. Please remember, I've had somebody recently do this in another class, but this is foiling. You can't just square the individual pieces, right? Okay, so you have x squared times x squared, which would be x to the 4th. In the inside, you have negative x squared. On the outside, you have negative x squared, so this is negative 2x squared. And at the end, I have plus 1. So it cleans up just a touch to x to the 4th minus x squared plus 1. And we haven't done any calculus yet. That was all algebra, right? It was. So in order to find where this equation now has a max or a min, what do I need to do? I need to take the derivative.
Can we just take the square root?
Can we just do what?
Just to take the square, so
The derivative of the square?
I'll just
He's saying, can you simplify it?
You can't. There isn't anything that allows you to, this is what I'm thinking you're asking. Something like this, where you separate the pieces of it. That's not possible to do, and let me show you a real quick example why. If I had 25 plus, no, it's not 25, I want 16 plus 9, and I were able to do that, that would give me 4 plus 3, right? But this would be the square root of 25, which is 5, and 7 is not the same as 5. So there's no way to distribute a square root or to simplify underneath a square root unless you have a quantity of the whole thing that's that's squared and cancels the square root out. So unfortunately we can't. That's a total bummer.
x squared minus x plus 1.
Do you mean you want to factor it? Is that what you want to do?
I think he's talking about like squaring the whole thing to get rid of the square root.
Okay, if you square the whole thing, you also have to square volume.
Okay.
And that's a problem. Because then we're going to be doing implicit differentiation. Do you want to do that?
Probably.
No, probably not.
I mean, I don't know how to do it, but I'm going to take a look at it. 'Cause I don't.
We did it before. We've done implicit differentiation in the last section. Remember x's and y's on the
Oh,
same
yeah.
side of things?
No. I'm
Yeah.
hard pass.
That's what we would be doing if we squared both sides. So unfortunately, we just have to go back to brass tacks and go for it. And we actually have to do it the way it's done. All right, so let's take this derivative. This is to the power 1/2. So we can think about it that way anyway. So forth. So I've got 1/2 x to the 4th minus x squared plus 1 to the negative 1/2. What's the derivative of the inside?
4x cubed minus 2x.
Excellent. So if I set this in a fractional form again instead, I've got 4x cubed minus 2x over, I've got a 2 down here because the 1/2 in front, and I've got a square root of x to the 4th minus x squared plus 1. And I also have, notice, a 2 here and multiples of 2 in the other location, so I can simplify those as well. So this becomes 2 on the bottom becomes a 1, the 4 becomes a 2, and the 2 becomes a 1 here. So this is 2x cubed minus x over the square root of x to the 4th minus x squared plus 1. All right, so any questions to that point? Okay. We need to figure out whether this is equal to 0, which means the numerator being equal to 0, right? So my numerator is actually a power of 3. Okay, it's cubic. So what do I have to do to solve something like this? Right, we'll factor. So I can factor out an x. This is 2x squared minus 1 now. The first piece gives me x equals 0. Right? The second piece gives me something else. X equals 0 is already a point that I considered. Right? It's this point right here. Maybe I'll do it in a different color so you can see. It's this point. If x is equal to 0, that's where I am on my curve. So that's already a point that I'm having under consideration anyway. The other one has to be set equal to 0. I've got 2 2x squared then equal to 1. Then what? Divide by 2. So this is x squared is equal to 1/2. And take the square root. And when I take a square root here, I can have negatives because this is just negative side of the graph. So I will, in fact, have a plus or a minus square root 1/2. And if you remember from trig, to rationalize this, you would multiply the numerator and denominator by square root of 2. So this gives me plus or minus square root of 2 over 2, which should be a familiar value to you, right? 45-degree angle kind of stuff. And I have 2 possible values. So I don't want to take a second derivative of this particular function, do you? Mm-mm. So I'm going to do a design chart. I'm going to put my negative square root 2 over 2 on it, my 0 on it, and my square root 2 over 2 on it. And we're going to try and find a value between each of those. So roughly, what is square root 2 over 2? Do you remember? 0.707. So what would be a number smaller than that? The negative 0.707. Okay. Hang on. The negative one first, yeah. How about negative 1? Will that work? And then I'll do the negative 0.5 that you were suggesting, Matt. And then we can mirror this with those same values, but positive on the other side. So positive 0.5 and then positive 1. Okay, so we're going to take each of those 4 values that are in red there, reddish, brick color, whatever, and we're going to put it into one of the forms of the derivative. So you can put it into here if you'd like. You could put it into here if you'd like, the cleaned up one that we have down here. It doesn't make any difference. Honestly, you could just put it in where? Do you know? On the top, because what do you know happens on the bottom? It has to be positive because it's a positive square root. So the value on bottom is automatically positive, which means we could just look at what happens on top, and that would be the easiest option instead. So what happens when I put in -1? You get a negative. Okay. What happens when we put in -0.5? A positive is correct. How about positive 0.5? Good. And positive 1? Positive. All right, this is all about increasing, decreasing. So negative is decreasing, positive is increasing. The question asked the closest points. Closest means that I'm going to minimize the distance. So which of these points of the 3 that are listed is a minimum? Negative square root 2 over 2 and square root 2 over 2. Both of them are, right? There's one more catch. It said to minimize, find the closest what? Point. This is not an xy pair. These are both values for x, right? These are 2 points, 2 values for x. But if I want the pair, if I want the point, I need the y value as well, right? So I'm out of screen space, but I've got a square root 2 over 2, and I've got a negative square root 2 over 2. How do I get the y value that's supposed to go with it? Original equation. What was the original equation that we're referring to right here, real quick?
Y equals x squared.
Good. I don't want you to think we're talking distance here. We're not talking distance. It's the y equal x squared. These are x values. So what happens when you take square root of 2 over 2 and you square it? You get a 1/2. You do. Works like that. And if you do it with a negative, it gives you also positive 1/2 because the negative cancels out. So I have 2 answers to this question. There are actually 2 points that are the closest point because the graph is symmetric, right? That should make sense. And they are at square root 2 over 2 1/2 and negative square root 2 over 2 1/2. Any questions on that one?